On the next few slides, we'll talk about normalization, and we'll show that once the wave function is normalized, it will stay normalized forever, no matter what. Previously, we just learned that the square of the absolute magnitude of the wave function represents the probability density of finding a particle at a position and at a given time instant. Under the framework of separable solutions, we know that the probability density function is stationary, meaning the function used to describe where the particle is likely to be found is never changed. It is solely determined by the spatial part of the total wave function in a separable solution. Because we are talking about the probability density function and the particle has to be somewhere in space, the probability of finding the particle in space must be unity. This means that the particle has got to be somewhere in space. Then the integral of the probability density function, when carried out over all space, must be equal to unity. It must be 100%. So the first expression on this page bears the physical meaning that we just talked about. It imposes a restriction, in fact, to any physically acceptable wave function when solving Schrödinger's equation for a given potential energy distribution and boundary conditions. And without this restriction, the statistical interpretation would be nonsense. Please also note that dr cube is a general expression for a differential volume in all coordinate systems. For example, in Cartesian coordinates, we have dr cube be equal to dx times dy times dz. Before we formally introduce the definition of normalization in quantum mechanics, we note that if psi of Rnt, the total wave function, is a solution to the Schrödinger equation, so is A times psi of Rnt, where A is a constant and can be in general a complex number. This is easily seen that if you substitute A times psi of Rnt into the Schrödinger's equation, you will always obtain the original equation by eliminating the constant A from both sides of the equation. So normalization in quantum mechanics is a process of choosing an appropriate constant A so as to ensure the equation shown at the bottom of the page is satisfied. With the normalization condition stated, we further introduce two terminologies associated with it. The first one is the so-called quadratically integrable or square integrable normalized function. It is a function that satisfies the normalization condition. A good example of the square integrable normalized function is the sine or cosine function, which we have seen when solving the problem of an infinite potential well in your undergrad semiconductor physics or modern physics course. On the contrary, when a solution is said to be non-normalizable, it can be either a trivial solution, meaning the wave function is simply zero, or a solution that doesn't satisfy the normalization condition. In either case, such a solution has to be rejected because they bear no physical meanings. But suppose we have normalized the wave function at time t equals 0. How do I know that it remains normalized as time goes on and the wave function evolves? In other words, if the wave function keeps changing, which it does because of the presence of the time dependence term exponential to the minus I omega t, and you keep renormalizing the wave function, then the parameter A, as we have talked about on the previous page, must also be a function of time. It is no longer a constant. And the new result you obtained for the renormalization purposes will no longer be a solution to the Schrödinger's equation. Fortunately, the Schrödinger equation automatically preserves the normalization of the wave function. Let's take a look at how it works on the next 3 slides. Okay, to show that once we obtain the normalized wave function, it remains normalized indefinitely, we consider the one-dimensional case for simplicity. When we say remain normalized indefinitely, we mean once you get the normalization done at any time instant, for example, at time equals 1 second, the normalized wave function stays as it is forever. We start from the time derivative of the normalization condition as shown here. The key point is that if we can prove the total time rate of change of the normalization integral is 0, then we know that the normalization condition doesn't change with time. Please note that going from this expression to this expression, we have moved the total time derivative into the integral as part of the integrand as shown here. And the reason for this is that the wave function itself is a function of position and time. We then recall that the absolute magnitude of the wave function squared can always be expressed as the wave function times its complex conjugate. So the partial time derivative of the probability density function can be expanded as shown here using the chain rule. For the 1D case, we know that the Schrödinger's equation can be expressed as shown. We then rearrange terms to obtain the partial time derivative of the wave function and its complex conjugate as shown in these 2 equations. We substitute these 2 equations into the partial time derivative of the probability density function. We end up with the expression shown at the bottom of this page. And if you take a closer look at the expression shown here, we have partial over partial x, I times the reduced Planck constant, h bar or h slash, divided by 2m. So this term is a constant. Then it becomes very important to handle the 2 terms within the parentheses as shown here when we apply the boundary condition, which we're going to talk about in more detail on the next slide. So we arrive at the expression shown here for the total time derivative of the normalization integral. We observe that the first term within the parentheses is the complex conjugate of the wave function times the partial derivative of the wave function with respect to x. The second term is the wave function times the partial derivative of the complex conjugate of the wave function with respect to x. We then apply the boundary condition which states that the wave function has to go to 0 as x approaches plus infinity. This will make the first term be equal to 0 and also the second term also be equal to 0 at x equals plus minus infinity. We end up with the final result as shown here. The total time derivative of the normalization integral must be equal to 0. This means that the normalization integral must be a constant, which means that it must be independent of time. So the normalization integral must be time independent because the probability of finding the particle somewhere in space must be unity at all times. I think this is the ultimate physical meaning of the time independent normalization condition.